So just to give you a flavor, more pictorial flavor, here's a molecular dynamics, and the target is not just to develop something that will run on a single molecule, but to just be able to simulate the entire system of proteins. And this is, so these large-scale simulations require, of course, very large machines, because, of course, not all the molecules fit in memory. Of course, we need the computational capability, but we need these to simulate cells and membranes and also like enzymes attaching to proteins, but we need to cover very many cases of that. Environment. So K Computer was one of the first to do this whole Earth simulation, climate simulation at sub-kilometer. And sub-kilometer simulation is very important because then you don't have to, because the cloud models, if you want a very accurate cloud model, you need to go down to sub-kilometer resolution. But this is, of course, very hard. And so we have the code running on the K, but of course, to do the integral over 100 years, which of course the target will require a lot more flops. And then so the target was to speed this up by a factor of 100. Medical. So this is a heart simulation, mechanical heart simulation, but it's not just mechanical. What the teams have done is to basically simulate a heart as a compound of a cellular structure. So they have these micro cells that which are elastic, just like real cells are. So see, these are simulating real muscles at the cellular level, but also you simulate the veins, you simulate the electrical pulses, because there are these cardiovascular systems obviously operate on electrical pulses. So, but very accurate renditions of the heart allows you to do kind of what-if scenarios, like what happens if the blood gets clogged, when you have an anomaly, what happens if you do surgery, what will be the effect, and so forth. So the idea is eventually we'll be able to simulate these organs in order for diagnostics and also for treatment. So this is very important. And also, this is similar to climate, but now we're doing weather. So for weather, we need to have real-time components. So we need to have these assimilations with data. So now the world is moving to converging or assimilating the high-end observational data in real time with computation. And again, weather being one of the very obvious targets. And so one of our teams, we're working on this data simulation. So this is Kobe, the Osaka Bay. And the left-hand side is observation. That's the amount of precipitation. And this is, so 3 other scenarios. So this is the one that was done with 100-meter resolution and with the data simulation. But this is looking 30 minutes ahead. So if I rerun the animation, you'll see that compared to simulation without data simulation, since it's a chaotic system, just goes wild and there's nothing matching reality. Even with the data simulation, if it's low resolution, you don't get the exact same type of result. But with high resolution data simulation, you can get very accurate forecasts, like 30 minutes ahead to, for example, forecast these immense downpours, which is actually happening right now in Japan. And data, graph analytics is important for science, but also for supporting stuff like social networks, also like bank financial transactions or detecting frauds and so forth. So we've been working a lot with graph analytics. And so one of the benchmarks is Graph 500, which is basically trying to do breadth first search on a very, very large Kronecker graph, which is a similarity graph, which is representative of the graphs that are you typically see in a social network. So the Graph 500, when it was started back in 2010, one of the authors of the Graph 500, our good friend Rich Murphy, who's now at Micron, he predicted that basically you'll see a very different list from the top 500, which is a LIMPAC benchmark, which was compute dense linear algebra centric. So that was his prediction. It's sparse. It's a sparse problem, and also the compute pattern is totally different. But when you look at the top graph 500 now, you'll see that you don't see any clouds that you might expect, but you see the familiar faces you see on the top 500. And in fact, we've been dominating the list for the past 4 or 5 years. We've been the K computer has been number one, and it'll retire as a number one machine, which is quite rare in this field. Very rapid progress. But it'll retire as a number one machine, and this is still faster than any of the top machines in the world, which of course has higher LIMPAC numbers. But K has been the de facto number one. But why is that? Well, because these machines may have very high flops, but K has very high bandwidth. Remember I told you that in HPC, bandwidth is a king, especially with sparse problems, and there's no exception for graphs, for graph analytics. In fact, when you do the analysis, of course, the problem is very much memory bound, but also very much network bound, because you have to basically, when you traverse the graph, you have to do lots of data exchange with your other nodes. So when the problem size is small, the amount of compute is in the dark blue is fairly manageable, where the light blue is communication. So compute is actually larger than communication. But when you get to really, really large graphs, and these really, really large graphs are starting to show up everywhere, then the problem becomes network bound. So in fact, at 65,000 nodes on the K, it has become so network bound, about 3/4 of the time is being spent on communication. So, our achievement is due to two things. One is, of course, the K computer being designed with bandwidth in mind, both memory bandwidth and network bandwidth, not artificially pushing the flops. But also, of course, one of my students, who's now here, and also my collaborators at University, also IBM, T.J. Watson, we were able to come up with an algorithm that will make optimal use of the available bandwidth in the system. Okay? So with these types of applications, the co-design went on, and we came up with a chip that I showed you. And again, I don't have time to go into details, but just to give you a very high-level overview of what the chip is like. It's an ARM processor, like I said. It has 48 compute cores, and also 2 to 4 what I call the system cores for running the operating system to limit the noise. It's a brand new core design. Integer has a near Xeon class, although not quite up to Xeon, but near Xeon class integer performance, maybe someone in it, like Haswell generation. ARM v8, ARM v8.2 to be exact, 64-bit ARM, and it also has embedded PCIe, obviously, but also embeds the network controller inside the chip. So an integrated network controller, which scales to 150,000 nodes and beyond. But also, it's a CPU, but with this integration. But also, the characteristics is also very much like a GPU. So we added lots of GPU-like features, like scalable vector extensions with various data types, scratchpad-like memory, just like you have on a GPU. So it works a little differently, but you can localize the cache. It has HBM2 on-package memory for very high bandwidth, and also the memory subsystem be able to sustain the streaming bandwidth. Also does what the stuff that GPUs don't do, like intra-chip barrier synchronization, very fast atomics, and other memory enhancements. So it's a CPU on one hand, like I said, it runs Windows and Word, but it's also very much like a GPU. in that they have very extremely high bandwidth to stream data out, stream data in, and be able to compute on them real fast. So, and okay, I won't have really time to go into details, so I'll skip. So if you're interested, if you're one of those architecture guys interested, you can look at these slides later. So, so what's the performance? Well, actually there are a bunch of benchmarks, but we haven't been able to disclose too many of them. Those should be forthcoming in the next few months. Once the chip becomes commercialized and starts showing up in various places. This is a very basic CFD benchmark, Himeno benchmark. So with that benchmark, here's a Xeon Platinum, which is this is a Skylake, and it just came up Cascade Lake, but the number will be slightly faster, but not much. So this is the Platinum, which is the highest end, and has, and in fact, it's a single node. It's got 2 CPU chips. So it's about 85 gigaflops in Himeno, which is, first it was a direct, very simplified stencil solver, direct solver. And this is Fugaku's A64FX CPU. And you can see it's about 4 times faster because it has high memory bandwidth. And since this is 2 nodes on a per chip, the Fugaku is about 8 times faster. And this is, in fact, Fugaku is faster compared to the SX Aurora, which is the NEC's vector chip, and also faster compared to the Tesla V100. So, this, again, so this kind of shows the effect you get when you optimize your architecture for HPC, especially with bandwidth in mind. On real code, of course, there are lots of other factors, like on WRF. This is a result of WRF, the latest WRF. And in WRF, of course, you have other effects, like you have not only the dynamics, but you also have it's not just a transport equation, but also you have to basically do all these physics. And both the transport equations and also the physics, they involve, things like boundary conditions, and there are lots of conditionals. So they speed up, and integer, then Intel is really good at that. So the difference becomes less dramatic, but still it's about 50% faster per node, or about 3 times faster on a per chip basis. And of course, this is a lot lower power. So on the power performance comparison, I can't give you the real exact numbers, but it's about a factor of 5 better than Intel. Oops. Okay, so this is what the machine looks like. That's the chip, that's the board, and that's the chassis. 384 nodes. It's all liquid cooled. The interconnect is 6-dimensional torus. It's embedded into the memory controller subsystem. So if you're, again, architecture geek, the NIC of the HCA being embedded into the network, into the memory subsystem allows you to do cool things like L2 cache injection when you do remote reads and writes, which reduce latency by about 30% in our measurements. So the latency, so the bandwidth is very high, like we get almost 40 gigabytes per second injection per chip, but also the latency is real low. So we get about 0.5 microsecond between 2 chips, which is about twice as fast as other interconnects. So with all that, again, we have more than 150,000 nodes. There's 384 per cabinet, so you can kind of do the math and see how many cabinets we'll have. And so it'll be a massive machine. It'll be very efficiently cooled using high pressure direct liquid cooling. And but the downside is, it's a very power efficient chip, but we have so many of them. We have to upgrade our data center to be about 40 megawatts, which is Google, Amazon size data center. Of course, we'll be much faster, but that's a consequence. But the NRE for the machine It really pays off because had we built this out of conventional commercial chips, this would have been, very, we had to build machines that are like 3 to 5 times bigger. And the cost would have been prohibitive. Okay, oops, little duplication here. So you'll see this. All right, so the remaining 10 minutes, I'll talk about the AI. Oh, so by the way, the programming environment is very generic. So it's just like using x86 cluster. In fact, it has containers, and we're working on all the AI frameworks, not just standard HPC, and work with ARM and on our own, of course, with Fujitsu on this. So, it's a very standard programming environment. So, about AI. So Japan was investing a lot in AI. In fact, 4 years ago, there was an announcement that there will be a significant government investment into AI, which is actually earlier than what the US government said. So I'm happy about that. The downside was because it was done so quickly, it resulted in 3 national AI centers, not 1. Why are there 3? I don't know, like turf war or whatever. We have lots of supercomputing centers, so that may be fine. So we have AIP, which is Riken's AI Center, our sister center. We have AIRC, which is AIST Center, and we have UCRI, which is both communication. And each of the centers have their own expertise, but each are very well funded under the national program.